All right, recording is rolling. Welcome to Friday. So a bunch of you guys just turned in the trigonometry page. I just polled you guys, see how you guys feel about that. Some of you guys feel really good on this. Some of you guys say, I probably need a little extra time, a little extra help. Some of you guys feel a little bit more lost. So I'm going to amend today's lesson and do a little bit more triangles with you guys. So you say that again. Okay. So next week we'll start kinematic motion, which is like displacement, velocity, time, acceleration. So we'll talk about. Monday's going to be a weird day. Okay, so Monday, I'm actually not going to see you guys Monday. You're going to be your first period for 3 periods worth, right, 3 classes worth. Skip periods 2 and 3 altogether, and then you'll pick up at your 4th period class, and then go on from there. So it's going to be a weird day. You guys don't need to worry about AP stuff. Okay. Yeah. So I'm not going to do anything too vital with my other classes because I'm going to see you guys, and I don't want you guys to really get that far behind. Yeah. So let's do this. Let's do a little bit of dimensional analysis, and then I'll do a little bit more trigonometry with you guys to help you guys out. All right. So dimensional analysis. You might remember this from chemistry. This is good for like converting units. It's also good for being able to construct proportional equations like proportionalities if you know how variables and units work. So let's do some examples. Question 1, how many days are in 1 million seconds? 1 million seconds. How many days is that? Okay. So if you know how to solve that, then go ahead. Since the first days that I'm asking you guys, I'll go ahead and walk you guys through this one. Okay. Now, the way I'm going to solve this, I'm going to use these railroad tracks. This table with railroad tracks. Okay. Since you guys have been through chemistry, depending on who your chemistry teacher was, you may or may not have used this exact method. That's why I'm going to do this. Okay. So I'm going to start with this given value of 1 million seconds. Okay, so we know that that's on board. 1 billion seconds. 1 million seconds. And the unit seconds is just lowercase s. You guys remember that from yesterday? Okay. Now, I somehow need to convert that to days. Okay, so I'm going to put this through a series of conversions until the last step says some number of days. Okay. Hey, maybe I could go seconds to minutes, minutes to hours, and then hours to days. Is that a good roadmap? Right? Okay. So let's try that. Oh, how many seconds in a minute? 60, right? Now, see how it's kind of like a fraction being set up here? Like a fraction bar. You guys can see that emerging, right? Okay. So I'm going to do it this way. I'm going to say that 60 seconds, 1 minute. Right? So I write this fraction like this. Okay. Now, you guys know that 60 seconds is equivalent to 1 minute. I mean, they both describe the exact same length of time. Therefore, isn't this fraction really some value divided by itself? Right? And what is anything divided by itself? What's that equal to?
1.
1. Yeah. So isn't it true that I'm taking 1 million seconds and I'm effectively just multiplying by 1, which doesn't really change anything, right? But it's set up in such a way that I'm swapping out the units. See how the seconds are set up to cancel out? So if I do 1 million divided by 60, that's the equivalent number of minutes. Is that? Okay. Let's just repeat that process down the line here. What do you think the next step will be? What divided by what? 1 hour, 60 minutes. Exactly. Boom. Right? Because again, since those are equivalent values, right, the fraction is just equivalent to 1, so you're not really changing anything. But the minutes, now we have an equivalent number of hours. Ooh, what's the last step? 24 hours equivalent to 1 day. Exactly. Hours cancels. You see all the units cancel except for days. Right? That means that this now represents the number of days. So you're going to multiply everything across the top and then divide down these numbers down here. So that's in the calculator. What's 1, 2, 3, 4, 5, 6? Here's 1 million divided by. Now here's where you gotta be careful to communicate correctly with the calculator. I'm going to do it this way. I'm going to open a parenthesis and then multiply these 3 guys together, but they're all in grouped together in parentheses below the fraction, below the. So 60 by 60 by 24, and then close parentheses, so it's all grouped together in the denominator. That is equal to 11.57 days. Okay, so there you go. There's okay, so 1,000,000 seconds is about a week and a half. Okay, you guys go back. Next question: how many years is equal to 1,000,000,000 seconds? 1,000,000,000 seconds. How many years is that? See, you sort of got a head start already with what's already there, right? See, okay, well, see how to model that. You guys can get that yourselves. Well, we'll start filling this in. Hopefully you guys are a couple steps ahead of me. Has anybody got the answer by now? Who's got the answer? Anybody got it? Okay, so everything I've written so far is really just a repeat of the process from last one. If that you need one more step, which is whatever what. Every 1 year, because the question is like how many years, right? Is equal to like 365 days. Let's try this out. Okay, so we take 1,000,000,000. 1,000,000,000 is also 10 to the power of 9. You might remember that from yesterday. 10 to the 9, I could just say that, right? Divided by, open parenthesis, and then these four numbers together. 60 by 60 by 24 by 365. Okay. See, we're just having seconds, minutes, hours, days. The only unit left on the board is years. So this describes the number of years. 31.7 years. 31.7 years. Look at there. Look at there, right? Okay. Wow. So 1,000,000 seconds is about a week and a half. 1,000,000,000 seconds is like 31 point something years. Wow. Pretty crazy.
Wait, I don't get it. I don't get the answer.
Okay. So yeah, let me do it again. So I set up this railroad track table so that the units all canceled except for years, which is the question, like how many years is this, right? So I start with my given, 1,000,000,000 seconds. Then say 60 seconds is equivalent to 1 minute. So see, I could have gone 60 over 1, but then that wouldn't have, it would square seconds over a minute, which doesn't make sense. But if you do 1 minute over 60 seconds, now the seconds cancel, just like before. Okay. Okay, so now at this point in the table, that represents how many minutes equivalent to 1,000,000,000 seconds. Okay. So we're working our way towards years. So I know I can go minutes to hours. So 60 minutes equivalent to an hour. Now the minutes cancel. So that's how many hours. I can go hours to days. 24 hours is equal to 1 day. The hours cancel. Okay. And then finally days to years. So there's 365 of those. Okay. So now the days. Okay. So now all the units cancel except for years. So I know that this does answer how many years. Okay. Now I multiplied all the numbers at the top. So it's 1,000,000,000 times 1 times 1 times 1, which is just 1,000,000,000. Okay. So I have 1,000,000,000. And then divide by, and then all the stuff down here. Now, the way I did is open a parenthesis and then multiply these guys. 60 times 60 times 24 times 365. And that is 31.7 years. Okay. All right. Let's say you guys are going to host a pizza party. And there are going to be 14 people at the pizza party. And you're trying to figure out yourself, I wonder how much I need to budget for pizza. How much do I need to spend on feeding 14 people, maybe you and 13 friends? Okay. So you figure, well, Hey, what do you think you'd have to consider? What are some values you'd have to know to answer that question? The cost of the pizza. All right. I'll tell you guys the pizza costs $9. So $9 per pizza. That's a fraction, right? Ratio. What else do you think you'd have to know? Yeah.
Possibly like the slices per box.
Oh, okay, yeah, let's slices per pizza, right? Let's call it 8 slices per pizza. Right? There's one more thing you'd have to know or estimate, which is what?
How everybody's gonna eat.
Yeah, how much is everybody gonna eat? Right? So I'm just gonna copy it from my notes. Let's say you come up with like 4 slices per person. All right. Yeah. At that point, now there's enough information where you guys see these bottom 3 numbers are fractions, right? There's enough information you can calculate how much to budget, how many dollars. You guys go ahead. Give you guys a head start. Give you guys a hint. You're going to start with your given value, 14 people, 14 persons. Okay. You got to go through a number of ratios. And at the end of the day, the only unit left on the board should be dollars. All right, let's move on here because I do want to put in some trick practice for you guys to take off for the weekend. Okay. So somehow I need to convert people to something else, and there's only one ratio that'll do that. You guys see this very last ratio, 4 slices per person? Okay. Hey, should I put the 4 on the top or on the bottom?
Bottom.
Well, I do need people down here, right? What if it is? What if we do 4 slices per person? See how the people's gonna cancel? So at this point, it would tell me how many total slices are being consumed. Okay, so 4 is gonna go on top. Okay, so now I know how many slices are in circulation. Is there another ratio that deals with slices? This guy right here. Where's the 8 going to go? On top or on bottom? Yeah, that's it. 8, because that's slices per every 1 pizza. Okay, so we got people canceling, now slices cancel. Okay, and now at this point, we know how many total pizzas I need to buy. Oh, hopefully this comes out to a whole number. It does. Okay. Oh, and what's the last step?
It'd be $9 on top and for 1 pizza on the bottom.
Exactly. $9 per every 1 pizza. And now the only unit left on the board is dollars. Okay, so calculator time. You're going to multiply across the top. That's 14 times 4 times 9. Or times 1 times 9, right? Great. And then divide by, well, there's an 8 down here. 1 times 8 times 1. So that's 8. $63. So 63 is the number, dollars is the unit. Yeah, there you go. There's how much you need to budget for you and your hunger friends. Oh, let's do. Yeah, let's do one more, and then I'll do a little bit more trig practice with you guys. Okay. So, yeah, dimensional analysis, really powerful tool. I think we do one more. That'd be just enough practice here. Let's say you fill up your tank and then you drive around, okay? And you drive. Yeah, I'm gonna make up some numbers on the fly. Let's say 300 miles to the next gas station. Okay. I'll almost never mention miles in this class, but just for this dimensional analysis example. Okay. And let's say you spend, let's say $25. Let's say $25 even filling the tank. Right? Filling the tank. and gasoline costs let's say $3.50 per gallon.
I wish.
All right, so let's run with those numbers. Suppose you have all that going on. What is the fuel efficiency of your car? The fuel efficiency. Fuel efficiency. Guess what would the unit for fuel efficiency be?
Miles per gallon.
Miles per gallon. Right? Hey, can you somehow rearrange these numbers so that the units will pop in place and you get some kind of miles per gallon out of this? Ooh, I got a whole number. Okay, these guys want to figure it out. All right, give you guys a little more time.
You divide.
Yeah, there's some dividing going on. Yeah, that's true.
300 like 350. Or
Yeah. See, how would you multiply it by the number so that maybe some units click in place, and at the end of the day, you're gonna get miles per gallon. Ooh, guys, should the dollars cancel out? Yeah, dollars is not a unit of fuel efficiency, so the dollars should cancel out somehow.
you divide 350 by 25.
What number did you get?
I got 42.
42. Yeah, all right. Aaron got it. Aaron got it. Okay. So I'm gonna put 300 miles on top. I'll tell you what to do. This particular example is not strictly a unit conversion, but you can use dimensional analysis to do exactly what we're doing, like as an exercise. Okay. So this is a little bit different category problem than the last few we've done so far, probably what you did in chemistry. But I'm trying to make this look like miles per gallon. So hey, miles, that pops in place in the numerator there. So we're off to a good start. Okay. I need gallons in the bottom. So hey, how about this ratio? $3.50 per gallon. Okay. Now gallons is locked in place where that needs to go. But we got this dollar unit. Or hey, maybe I should somehow divide that out. Put $25 down here. Right? Okay. Now, again, this is not really conversion like the last few were, so it's a little bit off the beaten path, but this will answer it for us. So it's a different kind of analysis. Okay. See how the dollars cancels? Okay, so I'm going to multiply across the top, take 300 times 3.50, okay, then divide by 25. That is, in fact, the number is 42, and the unit is miles per gallon. Aha. 40, I'll also call it 42 mpg, miles per gallon. Okay. All right, okay, you guys good with that? Okay. Yeah, this is a really powerful tool. Yeah, I have some other examples signed up, but let's do this. Looks like there's a sufficient demand to go back and revisit. So a little bit of trigonometry. So let's do that. Okay. Tell you guys what, if you want to pull your paper out of the gray tray, if you don't feel super confident about it and get a little extra practice here, then help you guys out a little bit more. So see there's some questions to ask you guys before I start this recording. Let's see, how do you use the protractor still? Remember, all these videos are on Google Classroom, so you can model exactly what I'm doing. Also, I did upload some paper protractors to Google Classroom, so you can print those out, use those at home if you like. Okay. But I'll do another wedge triangles with you guys, and then I'll do some from here. I think we've got enough class time. Okay. So how about this Lavoisier triangle? This real skinny guy right here. It looks pretty fun. Remember, each one of these triangles, 5 measurements, right? The 2 acute angles and the 3 sides. So let's get all the measurements first. And so how do I measure this side alpha? Well, there's two ways to do it. You can go clockwise or counterclockwise on the protractor. So I'm gonna take this node, this protractor, park it right on this corner, zero out this leg, okay? And then the hypotenuse naturally sweeps through the measure of the angle. See that? So I'm trying to get what's the size of this very skinny wedge right here. Okay? And it's just a few degrees. Now there's actually two numbers that sweeps through on the protractor. The outside number says 173. The inside number is 7, right? 10 minus tick, 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 3 is that 10 minus 3 is 7. So what looks correct? That little tiny wedge right there, is that 173 or is that 7? 7. 173 versus big old over here that I don't really care about. So Lavoisier alpha is indeed 7 degrees. 7 degrees. Okay. The other way you could have done this is turn the protractor upside down. Still park this node right on this corner. Zero out the hypotenuse in this case. And then, you can count the tick marks. That's 7 ticks. Going on the outside, 7 degrees. Okay. Now I have to get beta. So I could take this node, park it right on this corner, zero out that very short leg, and then the long leg, or so there we go. Okay. That looks good right there. Okay, then where's the single straight through? Looks like 83. Okay, looks like an 83 degree angle. So go up here, call us 83 degrees. Okay, now what about the other way you could use the protractor? And here's where there's a point I want to make. So I need to have some paper in the background. So let's get these notes right here. Okay. I told you guys last couple of days, some of these triangles are kind of small, like especially that side right there. So it might help using the protractor to go ahead and extend this leg. Watch this. Just extrapolate. You guys see this one? I missed it a little bit. Let me try it again. Start over. Looks a little better. You guys see it just extrapolate that leg. And what would that be good for? That'd be good if you use the protractor this way. If you zero out the hypotenuse, node, corner, zero out the hypotenuse, and so that's 0. And then sweep around. See, now it's still 83 degrees, but I needed that blue line extrapolation to get to 83 degrees. Okay. You guys covered that using a protractor? Okay. So examples last few days. Example right now. I'm recording this. I'll put this on the Google Classroom. Lots of examples using a protractor. Oh, I need my 3 sides. Now these are in centimeters, not inches. You guys are using centimeters, right? So this is 12.4, I think, maybe 12.4. Okay. If you measure it yourself, you got something slightly different. That's perfectly fine. But this should be pretty close to what I'm getting, right? Yeah, 12.3. That's fair. Side A, very short. I think I'll call it 1.6, maybe 1.6, 1.7, somewhere there. Okay. Then skip a few cells and go to side B. This is the last measurement. This is maybe 12.3, I think. 12.3. Okay, so those are the 5 measurements for that triangle. Okay. And remember how this table is organized. You see a very dark rectangle around these 4, and then around these 4 cells, because they all refer to the same side, but from different points of view. So C times sine theta. See, if you start with C, multiply by, or sine alpha, I should say, C times sine alpha, that kicks over to opposite of alpha, which refers to side A. So, and then calculation time. Here's your C, 12.4 centimeters, times sine, your alpha was 7 degrees. Oh, guys, alpha and beta. Shouldn't those numbers always be less than 90 degrees? If you got alpha or beta, it's like 100 something, then you got the wrong angle. So subtract from 180, and that should get you the right number. Okay, so these should all your alpha betas should be less than 90 degrees. Okay, so sine of 7 degrees in this case. I'm looking at 1.51, which is extremely close to 1.6. So that's good. How about C times cosine of beta? Now cosine beta, here's your beta. Cosine is like adjacent. Oh, hey, that also kicks over to side A. It's a different way of looking at side A. So what is 12.4 centimeters times cosine of 83 degrees? Oh, that's also 1.51, which is extremely close to my measured 1.6. So I am happy. And finally, square root of C squared by B squared. You guys can follow that as an operation, but you guys know that comes from Pythagorean theorem. Okay? So square root of 12.4 squared minus, and then B is way the heck over here, so 12.3 squared. That is 1.57, which again aligns really nicely with the measured value 1.6 centimeters. Right, so we're good. Okay. Now let's do the same thing except for side B. Now the measured value side B was 12.3 centimeters, but what about the sine, cosine, and then reverse Pythagorean theorem perspectives? Let's try it out. C times sine beta, opposite of beta. Oh yeah, that's totally side B. So 12.4 centimeters times sine of 83 degrees is 12.3 centimeters, which is exactly what the measurement was. Look at that. Okay. Next one, 12.3 centimeters times cosine of alpha, 7 degrees. Cosine alpha, that's adjacent to alpha. Oh, yep, that's also side B. So, what the heck? 12.4. I meant times cosine alpha. 12.3 again, centimeters. And reverse Pythagorean theorem. What's the square root of c squared minus a squared? So it's 12.4 squared minus, here's your A. Remember, A and alpha are different concepts, different units. So don't mix those up. Your A is 1.6 centimeters, but that was the measure value. I'll just play off that. 12.296, that rounds to 12.3, which is exactly in line with those other perspectives on the same side. So remember, those dark rectangle outline around those cells, each row should be pretty close to each other. I got a string 12.3 that's going across. Okay, good.
Can I finish this in the weekend?
Yeah, to tell you guys what, if you've been really confused so far and it hasn't worked out for you, you've been trying and it's like, yeah, if you guys want to turn this on Monday, that's okay. Oh, you won't see me on Mondays. Bring it to me if you can. Right.
Are you gonna post this on the
Yes.
Okay.
Yeah. So
Classroom. Okay.
this is being recorded right now, and this recording will go on Google Classroom.
Do we have the same answers for?
Everybody has different triangles, so you probably don't have my triangles. Right. Unless you have the Lavoisier triangle, then those would be the same. All right. Okay, we've got about 5 minutes here, so I can fit in. Here, do some more of these. I told you guys to do some of these, right? How about number 5? Let's try out number 5. Okay. What did I give you on number 5? I gave you the hypotenuse of the triangle, and also this alpha angle. Let's start by getting the beta angle. How do you get beta if you know alpha?
Subtracted by 90.
Exactly. Yeah. All right. So 90 minus alpha gives you beta. So let's do 90 minus 24. Right. That is 66 degrees. Right. Oh, I meant to mention that on the other side too. You guys just told me these two add up to 90 degrees, right? Right. That should also be true or very close to true on the other side of this page. So your alpha beta, it looks like my 3 examples here, they do add up to exactly 90, as long as they're pretty close. If it's 88, 89, 90, 91, right, your alpha beta should add up pretty close to 90 degrees. Okay. And mathematically, they should be 90. Right. So what are X and Y? Well, here's where I'm going to break out some paper. I'm going to take this picture of this triangle, blow it up real big, and do some calculations with you guys. Right. And really, it's supposed to be like vector components. You guys remember those hungry monkeys pulling on the bananas? So remember that monkey that was pulling up to the right? That's really what it's supposed to represent. So geometrically, it's a right triangle, but the physics application is it's going to be breaking vectors into components. Okay, so this triangle is not proportionally correct, but here's your numbers: 24 degrees. Okay, Z was 14 centimeters. Okay, that's a displacement vector. Okay, so what are X and Y? Right. Well, I know that Y is equal to the hypotenuse times sine of 24 degrees. I got a whole stack of notes here. Let's see if I can find real fast. Something like that. What's this? Come on, single page of notes, single page. All right. Nah, all right. Here, it goes like this. This side is always equal to hypotenuse multiplied by sine of 24 degrees. You guys remember SOHCAHTOA? Right. And then if you rearrange SOHCAHTOA a little bit, I gave you guys the notes a couple days back. Okay. Hypotenuse times sine of the angle spits out the opposite side right there. So that is what is 14 times sine of 24 degrees. That is 5.694. I'll round it. So 5.7 centimeters. Okay. How about this X side? Shouldn't this be equal to 14 centimeters times what? Cosine of 24 degrees? That's how you translate from hypotenuse to the adjacent leg. It's through cosine. And so what's 14 times cosine 24? That is 12.78. Okay, I'll round that to 12.8 centimeters. There you go. that completes that triangle. Okay. Hey, if this really works, then should Pythagorean theorem also work? A squared plus b squared is c squared.
Yeah.
Let's see if it does. What is 12 point? You know, these numbers are rounded a little bit, but with that in mind, what is 12.8 squared
146.
plus 5.6 squared? Oh, all right, getting that awesome. All right, so add this all up. Okay, get a really big number, and then I need to square root it. Hopefully, it's extremely close to this number. The square root of that answer is 14.01. Which looks a lot like 14. All right. It does work. So that was just the final check. So what do we get here? For X, we got 12.8 centimeters, and for Y, we got 5.7 centimeters. Okay. All right. You guys okay with that? Okay. All right. So if you turned already and you feel really good about your answers, then that's awesome. You're good to go. Yeah, if you really need the weekend to go back and look at the scan, I really care a lot more that you actually have the skill and you know how to do this, because this is a really good life skill to have, some geometry. And hey, someday maybe you guys are going to be building a fence, you need to buy some lumber from the store, and like, hey, how much do I need? Hey, I can get trigonometry that I remember back in high school. Right? All right, so we got about a minute to the bell. Let me go ahead and end this recording here and walk around and help you guys out. And any questions you guys have.